partnership project from Innovate UK. Today, he will describe about his project. Uh, Please start your talk, Dr. Minh.
All right. Okay, so we start. Hello, everyone. My name is Nghiêm Quốc Minh, and I'm working at the University of Manchester and for the National Center for Text Mining. And today I will introduce you about some applications of active and proactive learning that we have been working on in our center. The content of my talk is we have the importance of data, active and proactive learning, and some applications. So the question that we always have in machine learning is more data better? So in this paper, Scaling to Very, Very Large Corpora for Natural Language Disambiguation in 2001, there is a very interesting graph here. You can see that the authors, they compare different algorithms, very different algorithms with each other and on the test accuracy of the data. And on the x-axis, you can see that they increase the numbers of training data from 100,000 words to 1 billion words. And this is very interesting because they conclude that the algorithm is not so important. The more data we have, the more accuracy we have on the test data. And on 2011, if you know this person, he's Peter, the director of research in Google. He said that we don't have better algorithms, we just have more data. So is more data the better? So actually in machine learning, we have two cases where we have high variance. The model is too complicated for the amount of the data we have. So if we don't have enough data, we usually have overfitting. So the training error is much lower than the test error. So in this case, the more data we have, the better. And in the other case, high bias, where the model is too simple to explain the data we have. So in this case, if we actually have more data, usually we don't achieve better results. So if we have more data, it's not always that we achieve better results. But if we have better data, then usually always we have better results. So on the same quote, Peter also said that the more data beats clever algorithm, but better data beats more data. So on this talk, I will introduce a little bit about a method to create better data instead of create more data. So better data can mean you have less data, but you can lead to better results. So when creating a data set, usually we start with unlabeled data. So on the left-hand side, you can see that we have a lot of unlabeled data. And normally we will distribute these unlabeled data to different annotators. And then each annotator will work on the data that's assigned to him or her, and then annotate the data. Then we have a collection of label data. So this is the traditional way to create a label set, a data set with label. And then based on the created data, we can train a model. This method is very expensive and time consuming because we have to label all of the data points we have. And different annotators, they have varying levels of expertise and reliability. So some annotator, they perform better. Some annotator, they perform worse. And some annotator, they only have specialized expertise in very specific data point. For example, if we labeling name entity, some very good at detecting person names or organization names, but not as good as when they deal with location, for example. So in active and proactive learning, we have different strategy to label the data. From unlabeled data and different annotator, we have a central system where the unlabeled data will be sent to that system. APL is for active or proactive learning. And this system will choose which data point we need to annotate first. For example, this one. And then it will select which annotator is best to annotate this data point, and then assign that data point to the specific annotator or annotators. And then the annotator will annotate the specific data point, and then we use this label data to train the model. So we only have a very few data at this moment, but we still use it to train the model instead of getting a lot of data. And then from this model, we apply it to the unlabeled data again. And based on different querying strategy, we will select different data points to annotate and then distribute it to the annotator. And we have more label data and train the model again and apply it on the unlabeled data again and get more data and so on. So this iteration will iterate over and over until we get to a stopping criteria. For example, we have satisfied result, or we run out of time or run out of money for the annotators. So in this strategy, we can have different active learning query strategies. For example, least confidence, margin sampling, entropy sampling, both entropy, and so on. So these are the strategies that we use to select which data point we should annotate. So normally we label the points that the current model is least certain about what the correct output should be. Or we can have query by committee, where a variety of models are trained on the current label data and vote on the output of the unlabeled data. So we will have to select to label the points for which the committee disagree the most. And again, among those and for proactive learning, we select different annotator to annotate a specific data point. And we have to model the annotators. And then based on the models, we predict which annotator should be suitable for each of the data points. So this is the test result on F1 score on the test data and the iteration. So the blue one is random sampling, where we choose the data point randomly. The green one is we use the active learning strategy. And the red one is when we use the proactive learning strategy. And we can see that when we use proactive or active learning, we can reach the higher results earlier than random sampling. So this proves the effectiveness of active and proactive learning. So in the National Centre of Text Mining in the University of Manchester, we have different applications of the active and proactive learning methods. So the first one is we built a system for annotation for sequence labeling, and I play a short video about this project.
This video will introduce you to plenty functionalities and how to use it. Navigating to the Plenty page, click on Login. The login screen opens. Please enter your credentials to proceed. Click on Projects, Create Project to create a new project. This functionality is project page displays all the projects that you are managing. Use the drop-down selection below to choose the project you want to view. Create a new project. The system generates 2 annotators. One expert and 1 follower. You can add more annotators if you want. Select a label to choose the label for annotation. Click Delete to delete the current annotation. Click on to remove the previous annotation. Click Skip to skip the current sentence and rotate the next folder. Click Next to finish the annotation for the current sentence. The system will fill in new sentences for annotation. Request an account or obtain further information about Plenty, please contact us.
So we also have another system. for different purpose. Or the name of that system is robot analytics to assist in systematic review, where people can have a large collection of data, and then we screening the collection whether it's related to the research question or not, and then we use active learning to assist people in creating, filtering those screening data, and so on. So I'll skip that video, and this is our new one where we apply the same active and proactive learning for document annotation, where we can annotate the document with every document have a labels or multiple labels like this one. And that's it. Thank you for your listening. We are opening to questions.
Thank you very much, Dr. Min, for very interesting talk. Do you have any question for Dr. Min? Okay. And I have a question. Can you ask Dr. Min directly?
Yes, thank you for your talk, Dr. Min. And I have a question. Can we start with the weekly supervision data or distance supervision data instead of unlabeled data?
Yes. So if you have initial label data, then even if it's small, it will have.
What I mean that the weekly supervision data with annotate automatically by all the system. For example, that we have COVID-19 document and we can use some other NER name recognition to annotate the data, but that is not 100% is correct. So how can we fix the data?
Yes. Okay. So in this case, you can apply the strategy name the query by committee, where you have different models, different model for name entity, and then you use different models on your unlabeled data. You have different results, and then you can select which one that those model disagree the most, and then choose that one to have the annotation by human. Yeah, and then you can iterate again and again by retraining those model of yours. Is it clear?
Yes, thank you.
Hello. Hello.
Hello.
Yes.
Yeah, hello, Dr. Min. I'm very interested in your presentation. So it is my favorite thing. I want to investigate more my time in that topic. So I have two questions. The first question about, I can't remember exactly the numbers, slide number, but basically you mentioned about annotators. Are they a real people, right?
Yes. Yes.
So basically in your team, you need to have some expertise, some people working on specific domain where we apply machine learning, right? Apply NLP. Is that correct?
Yes. For example, in our recent project with the Lloyd's Foundation, we deploy the system, and they have the expert to annotate the data. So we need some human in this loop in order to get the better data.
I'm working on on kind of strategy, on kind of we have curators. Basically, they are expert in biologies. But the problem we're facing now is the data is too much, so it's difficult for them to curate or annotate a massive amount of data. So have you had any mechanism to speed up annotating data?
Yes. So the problem that active learning solve here is that we have to annotate a lot of data. So in your case, the curator, he had to curate a lot of data, right? And we only show him a few data points that he need to curate. Then the result is that he only need to curate a smaller set of data, but the result is still we gain a lot of accuracy from the curated.
Okay, so as a consequence, so the system propose just a few keywords or few data where curators or an annotator easily pick up, which is the most relevant information, right? So
Yes.
I think that so the last question is could you share with us a little bit how you how you annotate, how you analyze the data? So I'm working on that service. So we're working to collect abstract from literature, from scientific paper, and we want to analyze it, annotate it. So the key thing in your algorithm is how to analyze it, how to analyze the original data.
So what you mean by analyze? Because we have different words here. Analyze the data, where we read the data and feature and so on. Or you want to annotate the data, where we annotate a label to your data points?
So let's say you have you have data, unlabeled data, but how you get the unlabeled data? So I think simply put, how you get the unlabeled data from the large text, for example.
So unlabeled data, we just need to collect them by scraping the web, or take it from any other sources. For example, in our recent project, we have our partner, they get the data from their database, and then we apply those methods on those data. So it's just a collection.
Oh, right. Okay. I see. Yeah. Thank you very much for your answering some questions. Thank you.
Thank you very much. So we have another question from Tommy Anchi. So
can I thank you Ngọc. Hi, Doctor. I just need you to answer too, because I think that the time very limited. So the first thing is like in very beginning of your process, you consider to pick up a random data and start label it, and before you put in the model. So because it's very less data for the initial model, so it can create a lot of bias and very small variance. So how can you use those model can apply for the bigger data? The second thing is, how can you deal with the missing data from your data set? Thank you.
Okay, so actually, when we first the first iteration, we should use random sampling because we nothing to rely on at this moment. But later we can still by apply active learning strategy, we can still choose the better data for the model. So and we can also apply some heuristic, like we want to balance the label, the data font. For example, we have 10 on 10 data on one specific class. Then we don't want to select the class anymore. We want to select a new class. So we can even if the unlabeled data, the model chosen is this one, we need to switch to another one. So we can apply some heuristic on that to solve the unbiased or unbalanced data. And can you ask your second question again?
The second one is about the missing data from the data sets.
Missing data from the data set.
Yes, because for the growing data from a website or some whatever sources, you already have some missing data. And what do you normally do with that? You eliminate all the data, or you do any technique to like fill up the missing, like missing some part of the data in order to start your processing?
I mean, so you mean that when you collect the unlabeled data, there are a specific unlabeled data point where you don't have you have missing data, for example, missing a part of that data, right?
That's right. Missing a part of data, not like you have fully everything, just some part, like for example, just the data of the genetics problem. So some gene, they don't show clearly which part they have. So how you can deal with those?
Sorry, we haven't have any method to deal with that. But in general, when we collect the unlabeled data, we need to clean the data before we put to annotation. For example, if we have missing data, then we just need to filter it out.
It means you do it manually.
Filter based on some criteria. For example, if you normally we use the script automated filtering because the unlabeled data is very large, and we cannot do it manually.
Okay, thank you.
Okay, thank you very much. So, okay, so maybe we should start the finals presentation.
Thank you.
Thank you very much.
Okay, thank you very much again for Dr. Minh for share a very valuable real scenario about the annotation. Okay, well, and now let's move on the last speaker. I would like to introduce Dr. Trần Hưng Nghiệp. He have got his PhD from the Graduate University for Advanced Studies. Now he is a postdoc researcher at National Institute of Information. Today he will share with us his recent work toward efficient and expressive knowledge graph embedding for lean prediction. Please go ahead, Dr. Kip.
Can you see my full screen?
Yeah, I can see it.
Yeah, thank you. Thank you very much, Dr. Kwok, for your introduction. I am Hưng Nhật Trần from National Institute of Informatics, Tokyo, Japan, in Professor Atsuhiro Takasu's laboratory. Today, I will talk about efficient and expressive knowledge graph embedding for link prediction. This is not directly related to NLP. However, you will see that the technique are quite similar and the application have some overlap with NLP task. In this talk, I will first introduce the knowledge graph and overview the link prediction task and its application. And then we will look at the previous knowledge graph embedding methods for link prediction. And I will present some recent advances in efficient and expressive knowledge graph embedding. The knowledge graph graph that represent knowledge, and these knowledge are about multiple relationships between entities. In other words, they represent the multi-relational data. For example, in real world, we will see the ontology or the information networks or the user item interaction in recommender system or the task corpora can be seen as multi-relational data. And knowledge graph provides a standard format for this kind of data. It can be seen as a collection of triple H, T, and R that represent the relation R from the head entity H to the tail entity T. And it can be seen as a label and directed multi-graph. You can see an example here. There are some real-world knowledge graph. For example, the word net is representing the English lexical knowledge. Freebase and Wikidata represent general knowledge, and scholarly knowledge graph represent domain-specific knowledge, or the user item interaction represent the commercial activity knowledge. The link prediction is the task that predicts new triple given existing triple. And for example, we look at this picture, we can predict new link. So this paper cite this paper, where this paper published, and based on the existing links. The application is fill in the missing data or discover the new knowledge in recommender system, or we can form it as a reasoning stack on the knowledge graph or question answering multi-hop reasoning and other application. The previous method to solve this link prediction task is generally based on knowledge graph embedding. We can see a general architecture here, and there are three components. The first component, embedding lookup, will represent the entity and relation as the embedding. And the interaction mechanism will compute the matching score between these embeddings, and the prediction component will use the matching score to predict the existence of the triple. The previous method can be categorized in three main categories based on how they model the interaction. The neural network-based model are expressive but not efficient, and the translation-based model that use the translation between the embedding vectors are efficient but not expressive. The balance between efficiency and expressiveness can usually be achieved with semantic matching model. And in this talk, we will push this balance to a higher level. Now look at the previous method of semantic matching model. They can be seen generally as a bilinear map between the head embedding vector and the tail embedding vector using a matching matrix of the relation. And the drawback is that the mapping matrix here is a full matrix, so it's expensive and the model is prone to overfitting. To avoid this problem, the straightforward approach is to use diagonal matching matrix. You can see here, and it can be seen as computing the trilinear product between the head embedding vector, the tail embedding vector, and the relation embedding vector, where this diagonal is the relation embedding vector. And this is efficient. Now we look at some models that are built based on this approach. The RESCAN model are not efficient, as we have already seen. The Dismoon model are efficient but not expressive because the model can only model symmetric relation. It is because the mapping matrix is a symmetric matrix, and some recent state-of-the-art model try to have both efficiency and expressiveness by composing multiple small diagonal matrix into the matching matrix using different patterns here. So, but there are some problem with this. These patterns are manually designed, so they are potentially suboptimal, and they also complicated and difficult to extend and improve. So the question is, can we have a more systematic approach to this problem? Here we disclose that yes, we can do better. And to do better, we will look at the two key aspects of previous state-of-the-art model. First, they restrict the interaction with a sparse matrix for computational efficiency, and they use special interaction pattern by weight tying between the non-zero entries for model expressiveness. And to do this systematically, first for efficiency, we propose the multi-partition embedding. That is, we will divide each embedding vector into multiple partitions and only let the entries in the same partition interact with each other. This can be seen as a block diagonal mapping matrix for the bilinear model. Moreover, to have a high expressiveness, we will learn the interaction pattern on each block. And for example, using the Tucker tensor format. And this is a parameterized block diagonal bilinear model. Putting this all together, we will have the standard main model with block term format, as we can see here. And each partition will be modeled by Tucker tensor format, and some interactions scored together. We evaluate this system on 4 standard benchmark dataset, and the result is that compared to the state-of-the-art model in the recent year, compared to Rotate-E, the model is much smaller, but they achieve better or similar result on dataset. And compared to the another state-of-the-art model complex, the proposed model has similar size, but always have better or much better result. Here we show some connection to previous model. Our architecture is general enough to generalize on previous state-of-the-art model in semantic matching architecture. And we can see that the recent model are actually imposing some special interaction pattern on each block of our main model. In conclusion, in this talk, we have overviewed the knowledge graph as a standard format for general multi-relational data. and look at the link prediction task and some reward application in different domains. And we have seen that the knowledge embedding is an emerging research area, and we hope that new, efficient, and expressive knowledge embedding methods will open some new application in different domains. For more information, please refer to these two publications. Thank you very much. Your comments and questions are welcome.
Thank you very much for your interesting presentation. If you have any question, please ask in the QA session or raise your hand. Before you have question, I have a small question about your work. Your work is divide the data into many partitions, and I would like to wonder each partition can to run in a different different system or different model or different architecture or not?
Thank you very much for your question. As I understand, you are talking about model parallelization.
Yeah.
Yeah. As this, yes, that is a good suggestion. Currently, the model are designed in a way that they only need to communicate the final computation, as we can see here. Only the final computation are communicating between different partitions. So it is possible to implement model parallelization for each partition compute on different GPU or machine, for example. However, we haven't tried that yet. So if in the future, if we need to scale this model, we will consider that.
Yeah, thank you for your answer. And I have another question. It means you separate many participants, and the first participant can apply for deep neural network, for example, CNN. The second participant can run on another model, and after that, you merge the result in the end. Do you think it can work or not?
Thank you for your question. Currently, we separate between the higher level and the implementation level. For the higher level, the concept of this architecture can be used for, as you suggest, using different neural network architecture on each partition. But on the implementation level, we use a very simple model for each interaction on each partition here to make it more efficient, because if we use too large neural network for this interaction, it can be overfitting, or it can take very long time to run. So the current state-of-the-art approach for this task is use a very simple but justifiable model for each interaction.
Yeah,
such as we can see here the Tucker format.
Okay, we have one people raise your hand. Please.
Yeah, hello.
Hello.
Hello, Nghiệp. Thank you very much for your very nice presentation. So I'm interested in about ontology, apply ontology in machine learning. So you mentioned a little bit about ontology. So could you have any experience with using machine learning to annotate or predict ontologies or predict ontology-based data, basically?
Thank you for your question. In the ontology here, it depends on which domain we are coming from or which perspective we are looking from. The ontology concept can be a bit different. Therefore, ontology, I mean the ontology that represent knowledge, for example, the entity and other entity and how they relate to each other and the attributes of each entity. Is that the same definition of ontology that you are talking about?
What I'm trying to asking is, let's say we have a set of data set which is enriched by ontologies, right? So we applied supervised algorithms, to classify data sets. So how we integrated machine learning, and how or have you had any experience on how to integrate those things?
Yes, I see. So yeah, so I think we have the same definition of ontology. Yes, I have seen many work that using both the ontology and the other data to do some tasks such as question answering. And I have tried to, for example, see how the ontology can be built from the task corpora, or how we can use ontology for question answering, and that is possible to do that. There are some recent papers that interpret the language modeling as an ontology, on more specifically as a knowledge graph modeling task. And if you look at that, you can see that this is very natural to use ontology for example for question answering. But if you have some specific question, please ask that I can answer them specifically. Okay. Yeah.
Okay. Thank it. Yeah. We'll see. Yeah.
If you can, you need some other question, you can email us. Thank you.
I'll contact you via email. Yeah, I have some question and some comment on how we apply machine learning with ontologies. Yeah, especially in life science. Yeah,
that's interesting. Thank you.
Okay, so now it's 5:42. So I think we have a time about 5 to 10 minutes for the panel discussion. And here we have other speakers here, and except Professor Min. So if you have any question, you can ask directly. Is there any question to the speakers? So I think there's no more question. So thank you very much for joining us today. And I also would like to thank you very much for very nice, interesting, very nice talks from all the speakers. So yeah, hello, Wook.
Hey, hello.
Yeah, so would you please close the session?
Yeah, thank you for nice talk. Again, I would like to thank you very much for your own attention to our session. I'm very happy we received a lot of questions and discussion for our speaker. I hope all of you can get useful information from our session. After this session, we also can contact with speaker and our component via Slack. We hope we can to have many new collaboration between us and all of attendees. Again, thank you very much for your attention. And I think we should stop discussion in here for prepare for close ceremony in about 6 p.m. In this time, I try to answer some questions raised during the session. Again, thank you very much.